Hello, my name is Morris Cohen. I'm at Georgia Tech, and I'll give you a brief introduction about how we're planning to use a solar eclipse to study the upper atmosphere. So the region of the atmosphere that we are interested in is called the ionosphere. You can think about the ionosphere like it's the border zone between the Earth and space. Now this region is electrically charged, and the reason that happens is that you have X-rays and ultraviolet light from the sun that comes in and smashes against the upper atmosphere and rips apart molecules. And so you get this electrically charged gas called a plasma, and we call this the ionosphere. The ionosphere itself is split up into different regions. The part that we are interested in is the bottommost part of the ionosphere called the D region. So scientifically, this is a really tough region to study, and the reason is that it's very hard to take measurements. So we're talking about altitudes between about 50 and 100 kilometers. So you can try to launch a balloon. The problem is that if you get to about 50 kilometers, there's not enough air to sustain the balloon flight, so you can't get a balloon into this region. On the other hand, if you try to fly a satellite low enough, anywhere you get below about 150 kilometers, there's too much air, so a satellite will drag and then crash back into the ground. So this nebulous middle region here is sometimes called the Ionosphere because we really don't have a good way to take measurements, and therefore to understand what's going on. So perhaps the best means we have to study this region is to use radio waves. So let me show you. Let's say there's a radio station on Earth broadcasting, let's say gigahertz signals. For example, a GPS satellite signal being received, or a transmission to a satellite. These signals will go pretty much straight through the ionosphere. If you go down to lower frequencies, around megahertz, this is where, for example, AM radio stations are. These signals will basically bend, refract, and then return back down to the Earth because of this electrically charged plasma. Now, if you go even lower to kilohertz signals, or what we call the low frequency band, these signals reflect at about 60 to 80 kilometers altitude, and they also reflect off the Earth, so they sort of zigzag back and forth a really long distance. And because of that reflection, precisely from these D region altitudes, we can use these radio waves to study the upper atmosphere, in particular the D region of the ionosphere. So we know that these low frequency signals propagate all the way around the world because we've observed this from lightning for many decades. On this particular day, October 9th, 2015, there was a lightning stroke that happened in the South Indian Ocean. And what you're looking at is data from a receiver in Juneau, Alaska. That's really far away. That red splotch you're seeing is basically a short radio pulse in the low frequency band that comes from that lightning stroke. And in fact, we can actually observe this lightning stroke echoing around the world multiple times because of this very efficient reflection back and forth between the Earth and the lower ionosphere on the other end. So why does this all matter? Why do we care about the ionosphere? Well, as I mentioned, the ionosphere affects and has a big impact on radio communications, both for the aviation industry as well as for satellite signals, in particular GPS. We also know that these low-frequency waves can actually impact the space environment, and they affect something called the Van Allen belts, which are basically a band of very energetic particles that disrupt satellites and pose a danger to astronauts. In addition, there are some practical uses of these low-frequency waves because they propagate so far. They're often used for underwater and undersea communications, for navigation, and there have been some suggestions that it could be useful for forecasting earthquakes. So we work with what we call the Earth Ionosphere Waveguide, and again, that's basically a system to guide waves from any location all the way around the world based on these zigzagging reflections. During the daytime, when the sun's influence is strong, you get reflections at about 70 kilometers altitude. During nighttime, however, when the sun's influence very much diminishes, you get reflection at a higher altitude, so about 85 kilometers. Now we can see this transition very clearly in our data because there's lots of day-night transitions going around the planet. So here's an example. This is a radio station in Maine called NAA, picked up in one of our radio receivers in Dover, Delaware. And what you're looking at in this plot here is 4 days of data. And this is the strength of that radio signal picked up at the receiver. What you can see is that there's a very clear daily variation, nighttime, daytime, nighttime, daytime. And that's a classic signature of the sun rising and setting. So the sun's influence on the ionosphere is appearing and disappearing. The other thing that you'll notice in this data set is the last couple days of this plot there's a couple of spikes in the daytime data that clearly were not present in the early part. So these are actually solar flares. This is extra ionization that comes in from the sun and creates a lot of very strong ionization in the ionosphere, and that changes those propagation conditions, and you can actually see this as spikes. So what we're basically doing is we're using the entire Earth as a big X-ray detector to look at things coming from the sun. Now, the eclipse is a really special opportunity because it's the only time that we have a small spot of what looks like nighttime surrounded by daytime. Ordinarily, the day-night divide is basically half the globe, but here we have a little patch. What effectively happens is that you get a spot that will essentially scatter those waves in all directions. So if we pick up these scatterings, what we can essentially do is use the reflections almost like a radar reflecting off an airplane to characterize what's going on in the ionosphere as the sun appears and disappears. And this is the only opportunity that we have to do that. Let me give you an overhead view of how this looks. So this is, again, looking overhead. The green is a particular radio transmitter that we're looking at, and the red is our receiver. Ordinarily, we simply get a direct path from one to the other, bouncing back and forth in this Earth ionosphere waveguide. On the day of the eclipse, there's basically a second signal that scatters off this eclipse patch, and then it gets picked up at our receiver. So we get a sum of both detected in our radio instrument. So we know that this works because we've seen lightning do it. So here's an example. This is the signal from these two transmitters, NOK and NML, picked up again at this receiver in Delaware. On this particular day, there was a lightning stroke that happened basically along that path. And I'll play this video one more time so you can see that the moment that this lightning stroke happened, there was a disturbance in the signal strength, a very sudden disturbance, and then a gradual recovery over some tens of seconds, driven by the chemistry of the gas at upper atmosphere. And this corresponds precisely to when this lightning stroke happened. So what's happening is lightning is releasing a really intense amount of energy. It's disturbing the upper atmosphere and therefore affecting the propagation of radio waves through that region. So that's, again, using the ionosphere to characterize how radio waves can propagate around the world. So what are we planning to learn from all this experiment? Well, we want to understand three things. The sun's influence over the ionosphere. We want to be able to translate these lessons to understand how lightning disturbs radio wave propagation, and more generally, how are radio communications affected by these patch disturbances, particularly these sort of global communications, as well as any sort of ground-to-satellite or satellite-to-ground communications link. So we are planning to basically study this by putting up a network of transmitters and receivers around the country. So this map shows in blue are our receivers, and all the circles are various radio stations that we'll be looking at. All those gray lines, those are simply lines connecting transmitters to receivers. So that's a single slice that we have. Now that orange dot that you see moving across the screen, this is an animation of the eclipse as it sort of sweeps across our transmitter-receiver network. And all those red lines that you're seeing, those are basically extra scattered paths that we anticipate seeing only when that eclipse patch is there. So from all of those, red lines, we're basically going to be able to characterize or sort of image how the eclipse impacts the upper atmosphere. And from that, we have an understanding of how the sun influences the ionosphere. So I'll conclude by mentioning a fantastic team of students. I want to thank the National Science Foundation for supporting us, to various educational institutions around the country that host our equipment so that we can do this. And I wish you fun. I hope you enjoy the eclipse safely. And I wish you a day of clear skies.